Okay, I see some people are still joining, but it's time to start the webinar. So welcome everyone. Thank you for joining this month's DEIS webinar on the topic of space charge characteristics in nanodielectrics, presented by Professor George Chen from the University of Southampton in the UK. My name is Raphael Ferber. I am with the High Voltage Laboratory of ETH Zurich in Switzerland, and I have the pleasure to introduce Professor Chen for today's talk. Before doing so, I have a few housekeeping notes. So please note that the webinar will be recorded and it will be available from the DEIS Young Professionals YouTube page later. Also, if you have questions about the talk, please put them in the chat box or ask them directly at the end of the webinar by unmuting yourself. Then for the upcoming webinars, they will be held always on the second Tuesday of the month. And if you know an expert, or if you are an expert or know an expert who could speak at these monthly webinars, please get in touch, for example, through the LinkedIn page of the DEIS Young Professionals. So now I want to introduce today's speaker, Professor George Chen. Professor Chen is Professor of High Voltage Engineering at the University of Southampton in the UK. His main research interests are in the electrical characterization of dielectric materials and the study of the electrical aging of insulation materials. He is well recognized internationally as one of the leading experts in space charge measurements and its interpretation. And over the years, he has been involved in IEEE, IEC, and SIGRE activities, and is a fellow of IEEE and IET, the Institution of Engineering and Technology. Professor Chen has authored over 250 journal papers and 350 international conference papers. And we are happy that today he takes a short break from writing papers to hold this webinar and give us an insight into his research. And yeah, without further ado, I hand over to Professor Chen. Thank you.
Okay, thank you, Raphael, for your kindly introduction. And thanks also go to IEEE DEIS Young Professional Committee for the invitation. And this gives me opportunity to share my understanding on the charge dynamics in the nanodielectrics with a wide audience. So my presentation today is about the space charge characteristics in nanodielectrics. And here is my presentation outlines. I'll give a brief on both nanodielectrics and also space charge. And this will be followed by the charge separation mechanism and the key experimental evidence. The effect of the space charge on electrical performance of the nanodielectrics is proposed, together with a few influential factors. At the end, the conclusion are drawn. And if you look at this sort of SIM card, you can clearly see everything go to smaller. So that's why the nanodielectrics become sort of an important research topic nowadays. And so the first question we want to ask, where are the nanodielectrics come from? And to answer this, and we need to look at the nanotechnology first. Nanotechnology, by its definition, represents a group of emerging technologies in which the structure of matter is controlled at the nanometer scale to produce novel materials and devices that have useful and unique properties. And nanotechnology has found a wide range of applications already, including in medicine, energy, transportation, and aerospace, information, communication, and construction, etc. And you may ask, when was nanotechnology started? So here is a sort of very brief history of the nanotechnology. On that December of 29, 1959, physicist Richard Feynman gave a radical lecture at the American Physical Society meeting at a cantel titled "There's a Plenty of Room at the Bottom." At that meeting, and Feynman suggested it should be possible to make machines at a nanoscale that arrange atoms the way we want, and also do chemical synthesis by mechanical manipulation. And look back, and lots of them we have achieved, and probably even beyond already. So this is a lecture was widely regarded as the birth of the idea and the study of the nanotechnology. Of course, Professor Feynman is very famous, and he has received a Nobel Prize in 1965 for his contribution in the quantum electrodynamics. And so what is a relationship between the nanotechnology and the nano-dielectrics? And in the next slides, I probably just trying to show you graphically and the relation among them. So we can use this late shared structure and to clearly see the nanotechnology and involve the device and application and also the products. And this come from the nanomaterials, and nanomaterials including the nanocomposite, and the nanocomposite also including the nano-dielectrics. So what is the nano-dielectrics now? And this come back to sort of an initial proposal by Professor T.J. Lewis. So nano-dielectrics is a nanocomposite that applied in the field of the high voltage power equipment and power electronics serving as a dielectric material. The term of nano-dielectrics was first proposed by the later Professor T.J. Lewis in his very first paper and on nano-matrix dielectrics in 1994. And since then, the nano-dielectric material has been a very popular subject within the electrical engineering sector, and lots of research has been carried out. And so why we are interested in the nano-dielectrics, and let's consider where we can apply them. So here just show you some of the pictures, show you where potentially it can be used. And so in this case, we are using polyethylene-based nanocomposite to make the cable. And here we are using polypropylene nanocomposite for the capacitor. And in the GIS system, we are using epoxy nanocomposite. And for the machines, the generators, we are using enameled wire nanocomposite as well. So there's a plenty area we potentially could apply the nano-dielectric material. And again, I use another example when we consider the cable, give you the straight sort of a benefit when we have an increased dielectric breakdown strength. So assume we have an increased dielectric breakdown strength of the nanocomposite material. And if we consider this is a standard sort of a cable, insulation cable, and which sort of with a voltage V and the current carries the current I. And if we somehow be able to improve this material using nano-dielectrics by increasing its dielectric breakdown strength, then if we use the same size of this cable, and because now the material is stronger, we can apply the higher voltage. That means overall it can transport much higher power through the same sort of size of the cable. On the other hand, and because of the breakdown strength is high, we can thinner the insulation. And by thinner insulation, we allow more heat to dissipate through the insulation. And that means we'll be able to carry more current through the conductor. And for the same voltage, high current, then again, we can be able to transport more power. And if we're using the same voltage and the same current, and because the voltage, so breakdown strength material is high, so we can reduce overall size of the insulation. And by doing this, although we transport the same mono power as a standard insulation cable, but with much reduced size, and that means reduce the material, the dielectric material, and save the cost. So clearly, there are certain advantages of that. So because of that, and over the years, the research on nano-dielectrics has experienced a very rapid increase. And for that reason, and a dedicated journal and nano-dielectrics has been established, and in 2018. And this journal now has received its sort of first impact factor last year. And so now let's look at the more details. And there was a comprehensive review on nano-dielectrics by a CGRE working group. And the main finding related to the electrical performance can be summarized in this table here. So we can clearly see, and when we use a nano-dielectric material, and the partial discharge resistance is improved, and tracking resistance on the surface enhanced, and the life for the string and also have a prolonged. And we also see some breakdown strength increase or sometimes similar, and the space charge is suppressed, and the DC conductivity is decreased. And then with the permittivity and the dielectric loss, we also see the complicated the change as well. So within this talk, I mainly focus on the breakdown strength and space charge and the conductivity. And so because they are closely related to the charge dynamics in the dielectric material. When we look at this sort of a table, and caution must be taken, and in some case, and there are only two, when we observe this improvement, only two some are in the lower loading ratios, and some are in the high loading ratios. So for example, for the partial discharge, tracking resistance, tree lifetime, and typically you need a reasonable amount of a nanoparticle into the system. While for the breakdown, space charge, DC conductivity, and it's two in the lower loading ratio. So that must be careful. And so we have now introduced the nano-dielectrics, and let's move on to the space charge. And space charge research in solid dielectrics has experienced a very sort of a good period over the last 30 or 40 years. And thanks to the significant progress made in the measurement technique in 1980s. And we have gathered sufficient experimental data through the analysis of the data, and a few physical model has been proposed. And all this enable research to understand the charge dynamics much better. So when we consider the space charge in the dielectric material, and mainly we have two sort of sources. And the first is what we call through ionization. The second is through charge injection and through the electrode. And so here I'm going to sort of explain why we are interested in space charge. And so to answer this question, and we mainly look at the impact of the space charge on the local field. So here I'll show you, give two examples. And when we have this home charge form in the dielectric material, and when we say home charge is a charge polarity same as is adjacent electrode. So when we have a home charge formation, and this charge will produce its own electric field and therefore alter the field altogether. So as a result of that, and we have a very low field at the interface, but high field in the bulk of the insulation. On the contrary, when we have the heterocharge in the system, and we'll have a very high field at the interface, but lower field in the middle of the insulation. And so what is the space charge impact on the electrical performance? And here's a possible sort of impact. So when we have the presence of the space charge in the material, and it potentially could affect the short-term electric breakdown strength, mainly through the local field enhancement. It could also affect the long-term electrical performance and through the process we call aging. And it can also affect the electrical conduction through the alternation of the charge dynamics, and also the permittivity dielectric loss through what we call the Maxwell-Wagner polarization, and many others, such as partial discharge, and especially the partial discharge under the DC condition. So now, what is the relation between the space charge and nano-dielectrics? And based on the existing research, and several models has been proposed. And so if we have a charge in the system, and if we can eliminate this space charge in the dielectrical material, and then a better electrical performance will be anticipated. And especially for the material used for the high voltage DC applications, where we want to have a minimum or non-space charge in the system. And so based on the existing literature research, and many believe the nano-dielectrics can fulfill this expectation. And here again, I can use a power cable as an example. And this is research carried out by Japanese research. So initially, they are using this AC XLPE material and subject to the DC field 50 kV per millimeter. And over the time, you can clearly see the space charge being developed in the system. And once we have this space charge formed in this material, and you can also see the field distortion occur. And in this particular example, and because of the high amount of charge formed close to the electrode, and we have over 50% field enhancement in this case. And of course, that's not ideal when you're trying to operate in this cable under the DC condition. So in order to overcome that, and they have added some nanoparticles into such a material, and we make it into what we call DC XLPE material. Again, here we apply the same stress and observe the space charge. As you clearly see, there's a very little space charge form when we're adding this nanoparticle into this material. And as a result of that, there's a minimum field distortion, and so which is good for the cable design. And as a result of that, and they actually develop a 400 kV DC XLPE cable and with nano components. So we believe this component is a magnesium oxide. It is able to suppress the charge injection. So the next question we want to ask, what is the mechanism that leads into the charge suppression? Like many researchers over the years, and there are different mechanisms being proposed to this to explain this phenomena. So what is the true reason? And so that's something we're going to explore here. So over the years, we have this different mechanism being proposed. So such as a screening effect and a modification of energy barrier and the cancellation of ionization and the charge injection and deep trap formation after the introduction of the nanoparticle. So what is the true reason for that? And that's something we're going to have a quick look. So the first with this the research carried out by Professor Takata from the Tokyo City University. And they have done some experimental work, and initially with a LDPE without adding anything. And of course, when you apply the high field, you clearly see the charge injection. In this case, it's a positive charge injection and moving towards the cathode. And of course, if you don't do anything, gradually we'll have a very high field at this region that will lead into the breakdown. So then they're adding a small amount of this magnesium oxide, and that has some improvement. But when they're adding about the 1 PHR, about 1%, and you see significant improvement in the field. And now there's a very little charge injection into the system. To understand this, of course, and they also did some numerical simulation. And as a reason for the separation, they also have suggested that the induced dipole polarization around the magnesium oxide filler formed by DC stress application might play a role in the carrier trap side. And they believe, and you have formed some deep trap due to this introduction around this magnesium oxide nanoparticle. And further, the research from the Xi'an University and take this concept a little bit further. So when they consider when the deep trap are introduced into the polymeric dielectrics, and displacement of the Fermi energy level in dielectrics occurs, and that change the contact from the initial ohmic contact to blocking contact. Of course, when you have a blocking contact and there's no charge moving across the interface or the interface between the material and the electrode. And in the early research, and people also propose that potentially especially in the epoxy resin system, and where the ionization may occur, and so the charge injection and the ionization may neutralize each other. And as a result of that, less charge being observed, and therefore they propose what we call the cancellation of the ionization and the charge injection. And more people also study this phenomena use a TSDC approach, and also some of the surface potential decay approach as well. So over here you can clearly see, and when you introduce this zinc oxide in the LDPE system, you'll see more traps being formed, and in this case is more deep trap formed. And for the surface potential decay results, and they'll be able to calculate the energy level and for various samples, including this sort of addition of the nanoparticles. And when you see the addition of nanoparticle, you see this peak shift to the high energy level. And that is evidence of the high deep trap formation in the system. So that's what we say here. And so based on this, and we can summarize the formation of the deep trap due to nanoparticle is the most likely reason that lead into what we call the charge separation. So here is my version of how it works. And basically I divide into 4 simple steps. So nanoparticles themselves in dielectrics do not suppress charge injection, and they only introduce deep traps. So all the later effect is due to the introduction of the deep trap. So now when we sort of in the first step, when we apply the electric field to such a material, high field, and the charge injection takes place. And because of the deep traps in the system, and in the second step, this deep trap formed by nanoparticle captures the injected charge. So we call it trapped. And once charge been trapped, and these charges are difficult to move because they are need high energy to move around, and therefore they stay in the vicinity of the electrode. The third step is the inject charge will form own electric field, and that of course is in the opposite direction of the applied field in the region close to the electrode. And because of this sort of cancellation effect, and it will weaken the field at the interface and suppress the further charge injection. And here, of course, based on this description, and it's clear, and once you apply the electric field, there are still charge injected into the nano-dielectric material. They only stay very close to the sort of surface. And if the charge are injected to the nano-dielectrics, then the question is, why can we measure them directly using the space charge measurement technique? And to answer this question, and we need to look at the principle of most popular space charge measurement technique and the PEA method. And of course, we all know this method was invented by Professor Takada from Tokyo University in 1980s. And the Professor Yasutalaka has kindly sort of using a graphic and show the principle of this PEA technique. And so basically what we see here, we applied a pulse electric field, and this pulse electric field will interact with the charge and generate an acoustic wave, and that wave will transmit through and to the transducer, and we'll be able to monitor that response of that charge. And so here we are using this again. In the first case, if we have some space charge in the sample, and it will induce the positive charge on the two electrodes. And now if we apply the pulse field here, and that will produce a force, this charge will experience a force. And this force and will make the material move, and that will launch acoustic wave. And this acoustic wave will transfer and through the sample reach to the sensor, and then we'll be able to measure it. And so that's the principle of the PEA method. And in the case of there's no space charge in the middle, and we can also apply the DC field to produce charge on the two electrodes. And then again, we'll be able to apply the pulse field and form this acoustic wave, and moving towards the sensor, and then obtain this measurement. And of course, and this actually can be served as a calibration, because we can, if we know the permittivity of this material, and we know the voltage we applied, we'll know how much charge produced at the interface. So that we'll be able to calibrate the charge, and therefore know the position and or the amount of the charge using such a method. So now let's come back to this question. Why can't we see this injected charge in the nano-dielectrics? And in order to answer this question, and we will consider 4 scenarios here. The first, let's say there's no charge injection. So in this case, we apply the voltage across the dielectric material, and there's no charge injection. We only see the charge at the electrode. So of course, if there's no charge injection, the field in the middle of the sample is uniform. And so based on the principle of the PEA technique, we'll be able to observe some charge peak and with certain width. The reason we have certain width is the PEA system has a limited resolution, and due to pulse voltage and also the response of the piezoelectric transducer. And instead of have a 2D lined charge, and we have this observed peak with certain width as shown in this figure. And so that's the first scenario, that's okay. Now let's consider the second scenario where we have injected charge, but injected charge actually be able to move little away from the electrode. So in this case, And if you look at this electric field, and it's probably have a lower field at the interface, but slight high field in the bulk of insulation. But in terms of the PA measurement, and because this has a certain separation distance, and we'll be able to see this and in the actual PA single. So this represents this amount of charge in the bulk, right? So that's okay. We can do that. We'll be able to measure this and in the reality as well. And now let's consider the third scenario where we may have the sort of a nano-dielectric material involved. And that means we'll have a charge injection, but charge stay very close to the interface. And in this case, and if you look at the field, and it may be, again, we have a lower field at the interface and have some field enhancement in the middle. But due to the limited sort of spatial resolution of the PA system, and it's not possible to separate these two charges because they are very close. So as a result of that, and from the charge measurement point of view, we may still observe this similar like no charge injection. So that's a third scenario. That's what we most observed in the sort of nano-dielectrics with a lower loading ratio. And the fourth scenario is, okay, if that's the case, what happens if I remove the external voltage and we would only left this deep trapped charge in the system? That should allow us to measure it or observe it. But in reality, what we see there is again, and these two charges are still very close, and due to the limitation of the spatial resolution, and we still be able to see it. So that's why for the nano-dielectric material with a lower concentration of a nanoparticle, when we remove the electric field and we still don't see the charge, but actually it's there. So hopefully, and the above answer the question why we can't measure them directly use a PA technique. So that's the first thing. And the next issue I want to extend to the higher loading ratio. And so what happens if we have a higher loading ratio consideration here? So this is a typical lower loading ratio. What we see, the charge separation, the particle separation are large, and therefore that may represent the trap separation large. And as a result of that, and because of the deep trap and the large separation distance, it's very challenging for the charge to move around. So that's why we see there's no charge moving in such a system. However, and when we have a higher loading concentration of the nanoparticle, the distance between the traps become much smaller, and there's a possibility to have a tunneling apart from the hopping. And so therefore, charge going to start to move. So if this injected charge start to move into the bulk, and the injection will continue, because now the field here is going to not lower anymore, and it could be increased, and therefore leading to more charge injection. And as a result of this, and we expect the higher conductivity, because charge now can move in through the bulk and reach to the opposite electrodes. So that's a sort of extension model, or the model we extend it. And now you may ask, how are you going to validate this model? And so in order to do this, and we have designed a very simple experiment, and where we combine both PA measurement technique and also isothermal potential decay technique and together. And here we consider 3 samples, and is a blended polyethylene sample. And the first one is without any additives of nanoparticle, and we stress sample at 50 kV per millimeter for 2 hours in the PA system. So that allows us to monitor the PA or the space charge formation in such a material. And when we finish this for 2 hours stressing, and we transfer this sample to the surface isothermal surface potential decay system to monitor the sort of surface potential of the sample and its decay. So initially we start with the sample without any additive. So we clearly see there's a charge formation that we know these charges come from the anode, inject from the anode, and from sort of accumulate at the cathode region. And when we adding 0.5 weight % of silicon oxide into such a system, and we can clearly see, and there's no charge in the bulk, which as we probably expected, right? And if there's any, probably very close to the interface, which we can't measure due to the limited resolution of the PA system. And when we move into the high concentration, so let's consider 5% of this, and we also can see lots of charge now form in the bulk, and which is somehow consistent with the model we proposed. And more importantly, and if we examine the surface potential decay of these 3 samples, and bear in mind of the PA results, the one we barely observe any charge is with a 0.5% of this nanoparticle added. So in this case, we can clearly see, and it has a higher residue surface potential. And while for the highest loading, and there's barely, well, there's the lowest surface potential left, right? So the red one is a fresh one and without any additives. So this means when we have the highest surface potential, meaning there are more charge left in the sample. And because the surface potential is produced by the trapped charge in this sample. So hopefully, and this combined results strongly support the model. And to test this model further, and we also arranged the 2 layers of sample, and as shown here, use a PEA measurement. So one layer and have a lower loading ratio. The other one has a higher loading ratio. Based on our model, if that's the case, and we should barely see any charge moving through the lower loading ratio, but see lots of charge movement from the high loading ratio layer. And so actually the PA results confirm that. And so we are at the interface, and we see lots of this positive charge formation in such a arrangement. And if we swap these 2 layers around to moving this high loading ratio layer to the left, and then swap this to the right, and now we expect to see lots of elective charge form at this interface. And the PEA results clearly sort of show that. So based on this, and we can clearly see our model proposed and is be able to explain this observed phenomena. So I hope the presented experimental evidence convince you the descriptive model we proposed is acceptable to you. And so once we have this model, now we look how it's going to affect the electrical performance of the nano-dielectric material. So we mainly focus on the conductivity and space charge and the DC breakdown fields. And let's look at the conductivity first. So when we look at this, we look at how the concentration is going to have an effect on the change of the conductivity. So based on the model, we expect this type of behavior. So initially at a lower concentration, we see this charge separation, therefore blocking the charge movement, and that leading to the lower conductivity. But when we go to the higher concentration, and the tunneling effect come into play, and that's going to increase the conductivity and further with the concentration. So the experimental evidence we observed in the lower density polyethylene filled with silicon oxide particles, and clearly shows that trend. And more importantly, and at a lower field where the injection is less and the effect is barely to see. But once you increase the field to 40 and 50 kV per millimeter, and we clearly see this sort of a behavior. And for the high field, and when we go to the 10% concentration, we actually see the breakdown. And so we didn't get the value for that, and which is something interesting. So that is about the conductivity. What about the space? We can also look at the surface potential decay as well. So here clearly, and the black one is sort of without any additives. And then we have a different amount of the sort of silicon oxide added into it. And clearly see when we have the 0.5% and the surface potential and decay is very slower. That means it have a deep trap and is play into effect. But when we go to the high concentration, and because of tunneling, and the charge can move in through the sample quickly, and therefore decay much faster. So this is the fast one is if we go to 10%, and at end of sort of 900 seconds is a very little charge left in the system. So that's about the conductivity, influence on the conductivity. What about the space charge? And based on our model, and we can consider two scenarios, one lower and one higher concentration. And so in the lower, and we expect the separation of the charge. And so this is a without on-field blended sample, and this is with a sort of 2%, and with some sort of a surface treatment. And clearly see there's a, when you have a lower concentration, you'll be able to suppress this charge and to a very small amount. But when you go to the higher concentration, and what we observed there is we can see the charge injection extended to the bulk. And with this particular example, and we didn't get the 2 hours observation because the sample breakdown due to the high concentration. And as far as the charge amount in the system is concerned, the sort of trend is probably follow this type of trend and in the system. Now let's move into the DC breakdown, and we may expect the DC breakdown and to increase at the lower concentration and then start to decrease, and depend on the actual sort of interaction between the nanoparticle and also the surface treatment. And sometimes we may see the straight decline of the electric field strength with the concentration. So now we are moving further and look what is the potential factor affect this charge dynamics. So in summary, any factor that has impact on the charge trap on the trap lateral, like a depth, number, or charge velocity, will have impact on the charge number and the dynamics in the nano-dielectric material. And therefore, we can list a few of them. So the first is, of course, polymeric matrix you're using for the base, and nature of the nanoparticle you're using, whether it's zinc oxide, magnesium oxide, or silicon oxide, or alumina, and so on. They all could have impact on this interaction. And then the loading ratio, of course, and the size of the nanoparticles as well. And then nanoparticle dispersion is a very important factor, right? So because of sometimes we trying to improve the dissipation of this nanoparticle, and we intentionally do some surface treatment. And also, of course, the magnitude of the electric field is going to apply the charge dynamics, and the water or moisture absorption, and temperature, and so on. So in this presentation, I use 2 examples where we look at the surface treatment and the electric field impact on the charge dynamics. So here we have traced the sample at 25 kV and with 3 different samples. This one is on-field polyethylene, and this is a nano composite field with 5%, but untreated. And this one is treated, so you can clearly see the treatment make a huge difference, right? And so that's about treatment. But also we can look the field at 40 kV, exactly the same sort of sample. We are looking at this behavior at the 40 kV, and clearly, even now, when you even with the treated and sample at high field, you still see the charge injection into the system. So that means, and this various factors and potentially could affect the performance of the charge dynamics. And also we have made attempts to use a model simulating the conductivity of a nano-dielectric material with different loading ratio. And so in this case, and we consider the charge injection is through the Schottky mechanism. And when we consider the charge movement in the bulk of the insulation, apart from the Hoping mechanism, we also consider the tunneling, especially at the higher loading ratio. And of course, with the initial attempt, we assume the charged particles are uniformly distributed in the sample. And so we are using this conventional bipolar charge model, but we have introduced extra energy level in such a model, and represent the deep trap and means the introduction of the nanoparticle. So our initial simulation based on this model and has shown some promising results. So when we look at the current, that means the conductivity through the material, we see this initial decrease and followed by increase with the nanoparticle concentration. And when we look at the charge distribution with the particle concentration, and we see when we have a higher concentration, we see the charge extended more broadly to the bulk. And of course, and there's more work to do in this area. And so that at this stage, and I would like to draw a few conclusions and based on the above presentation. And the nano-dielectrics show a huge potential in future application in terms of its impact on the charge characteristics. And we can say the nano-dielectrics, nanoparticle bring in deep traps into the nano-dielectric material, and at a lower loading ratio, and typically you are leading to better electrical performance, and a high loading ratio, and you may see the increase in the conductivity and the lower breakdown strength. And charge dynamics will be affected by the introduction of the deep traps and many factors that can influence charge dynamics in the nano composite. And our initial work based on this model and show a promising future. Of course, systematic research is required, and especially on the impact of the applied electric field on charge dynamics together with the electrical conduction process. And one thing I want to also emphasize is sometimes you don't need to have a resort to complicated experimental tools, and sometimes lower and simple experimental design and plays an important role in the research. And the example is where we combine the surface potential and the PEA technique, and that allow us to have a better understanding about the charge dynamics as well. And I do hope and you can have something to take away and follow this presentation. And it comes to the end of my presentation, and thank you very much for your participation.
Thank you very much, Professor Chen, for this very informative overview. Yes, now we have time for questions. I see Okay, I will wait a minute to see if we have incoming questions in the chat. Just as an information, the presentation itself is available or will be available on the YouTube page. So the YouTube page of the DEIS Young Professionals. Yeah, if you have a question, you can unmute yourself and ask it directly or put it in the chat. So we have a bit of a general question. What would you recommend for future research on nano-dielectrics? Someone is asking for input on a proposal, I guess. We have this from the chat.
Yes, my sort of vision is it has a huge potential, and but we do need to understand the mechanism in order to better utilize that. And as I mentioned earlier, there are plenty of factors going to affect the performance of the nano-dielectrics. Therefore, all these factors need to be carefully controlled. And what I have seen so far in the literature, especially in the early literature, there's a lot of contradiction sort of results presented in the paper. And one of the reasons I guess is when you prepare the sample and some of them are not well controlled, and that could lead into totally different results. So just give example, and in my presentation, when you treat the surface or not treat the surface, you can get totally different results.
Mm-hmm. So very sensitive systems
That's correct.
to
Yes.
environmental factors. Okay, thank you very much for this. Then we have another question here. I can see one was a more practical question that said, how do you protect the measurement setup in case there is or you measure up to breakdown of the sample? That's a very practical question.
I think in the PA system, and because that's I think one of the good things with the PA system, and when you have the breakdown, you probably simply trip the high voltage supply, and because the measurement system is isolated from the high voltage, it's all sort of from the bottom electrode, which is earthed, and so you shouldn't have a major impact on your measurement system.
Okay, then I have another one from the chat which asks, does the trap level depend on the type of nanoparticle? For example, if they are conductive, insulating, or of semiconductive type, is there a correlation?
Yeah, the short answer is yes. And we believe that's mainly due to the interaction between the nanoparticle and the polymer matrix, including how you treat the surface as well. So there's a lots of factors potentially could affect the trap depths and also the number as well.
Okay, so it's not only about the bulk property, but also a lot about the interface. Then another interesting question, I think, is why is the space charge more relevant in DC stress? And here I might add that was also a personal question I had, because you also published some research on AC stress, and you also showed that also in AC stress, the space charge plays kind of a crucial role in the breakdown. Maybe you can elaborate a little bit on AC versus DC stress and the role of space charge in under these two stresses.
Yes, this is a very good question, and that's something I sort of take it very personally as well. So, of course, there's a general consideration that space charge is only DC issue, but in my opinion, it also is an AC issue as well. And that's one of the reasons we observe this lower breakdown strength for the AC. And in my opinion, is that space charge come into play and a very important role in the AC breakdown as well. So
Yes.
in my personal opinion, it's probably more important in the AC than in the DC. And
Yes.
that's a topic, and I'm trying to focus on at the present time.
Okay. Yes, I also found it very interesting that all of a sudden the space charge is of such fundamental relevance for AC systems.
Yeah.
Okay, then let's see. Yeah, if anyone has a question to ask directly, just unmute yourself. Then I might pick another question. Let's see. Yeah, here one question is also practical, talks about space charge effect seems to be very important for HV, high voltage applications. How important would it be for medium voltage applications? I guess here, yeah, the question is then about the electric field strength, but maybe you say a few words to this.
He had to unmute himself, I think.
Okay. Now it should work. That you can unmute yourself. Maybe you want to the one asking the question about high voltage and medium voltage applications. Maybe you can give a bit more details. Or otherwise we...
George should unmute himself.
Now it should be possible.
I think Warner has typed his questions in the box. He asks, how would nanoparticle show up rate show up in space charge curves as they visibly localist regions of high field concentration? He has typed them in the box, in the chat box.
Thank you.
Raphael, could you please ask George that he should unmute himself? He muted the microphone.
Okay. Where do I see it? I think now everyone can unmute themselves. At least that's what is shown here in my okay, let's maybe continue with another question in the meantime. So again, to Professor Chen, there's a question. Why do we measure both time domain and spatial distribution of the charge? Why is this important? It's from the chat.
Raphael, I really don't listen to him. I don't know whether the audience are listening to him.
Yes.
He can unmute his system by himself. So
yes, Professor Chen, can you unmute yourself?
right side of his name, right side of your name, you can just see it's a red color, and I
Exactly,
just click on
yeah.
that. Yeah, you just click.
I click on it and it says request.
Yeah, because he did by himself, I think.
But no response.
I think I have.
Professor Chen, you cannot unmute yourself? No. Okay.
Is it Raphael same that you want to unmute him, but you unable to do that?
Yeah, exactly. I'm unable to unmute him. I can just request that he unmutes
You can
himself.
see the list on the right side where we are right now. You can see your name. Professor George, can you see your name? Can you find it out your name? And right side of your name is a small microphone. It's in the red color and it's crossed. We don't hear you. Please can you write in the chat box? Oh, you can hear Professor. The audience can hear them. It's strange. Okay. Somebody have written on the chat box that they can hear. I would like to ask to the audience, can they hear Professor George?
No, we can. I think we cannot hear Professor Chen.
Okay, we cannot hear. So we can do one thing. I don't know whether this amount of questions can be answered through the chat box or not, but we will try to prepare one more, maybe in the future, similar kind of webinar that you can attend and ask the questions. And also we will consider all the questions has been set and asked by the audience. What do you say, Raphael?
Yeah, I think at this moment that's probably a good way to do it, because there will be similar topics in the future and we can take up some of the questions later.
We are extremely forward.
Now it seems,
now.
yes, now it
Okay.
works. Okay.
Welcome back.
Okay.
But that means I couldn't share the slides now. So, but it's okay.
It's okay, but we can just ask the questions had been written on the chat box, and I think it's still some audience over there. You shared shared already, so we can see your presentation now.
Okay. So I don't know why that's a sort of a, I didn't touch it or click anything, and the only thing I see, I'll mute by itself, mute by itself, and yeah, okay.
It happens sometimes.
So I'm happy to take more questions.
Okay. Raphael, can you go ahead? Yeah, there are a lot of questions on the chat box.
Yes, so I will go ahead with another one. So let's see. Yeah, there's one question that says, for a dielectric used as a capacitor, space charge will play a role in enhancing polarization and increasing permittivity, which would be an advantage in this case, unlike the role of space charge in an insulator. Is that right?
Yes, anything you'll be able to increase the polarization, and that potentially could be beneficial. However, and you must be bear in mind, and you don't want to produce a higher, very high field in the system that potentially lead to the aging and also the failure of the capacitor.
Mm-hmm.
So there's a limit you can go. And one thing I didn't mention earlier, because for the electric application, electric, and where we want to have more charge in the system, and so that's beneficial in that case.
Okay, thank you very much. And
thank you. Also, Rafael, I just would like to add one question here because it has been asked more than once.
For sure.
The person says, how potentially the deep trap charges in the nanodielectric materials will affect the local electric field enhancement if compared to the normal dielectric material? So how deep trap will affect the dielectric materials if the local electric field is increased compared to the normal dielectric material? I did not actually understand what he mean or she mean, but it has been asked multiple times.
I think I guess I know what the question is, and the potentially yes, and you may, by introducing these nanoparticles, you may increase the local field surrounding the particles, but hopefully the field enhancement there is not leading to the breakdown or anything.
Okay, I hope the who have asked the questions so got it, what he or she want to know. Rafael, go ahead, please.
So we have another one that says, how would agglomerates show up in the space charge curve, as they are localized areas of high particle concentration, but not globally? I don't understand fully the question, but probably you want to comment?
I guess it's about this aggregation effect, and of course, when we measure the space charge, and we assume one of the assumption we assume is under the area of the measurement, and we shall assume currently, at least, is assume is the charge are uniform and the system are uniform. But in reality, that may be not true. So in reality, you may see some amalgamation of this nanoparticle, and that could lead into significant local stress enhancement. And that's also potentially, in some cases, when we do the measurement, we sort of experience breakdown. And but while we assume it's uniform, but in reality is not well dispersed. So that, I think that's something always a concern for the nano dielectrics.
Okay, thank you very much. And yeah, let's take another one from the chat. Is in what respect or in what aspect is the charge recombination in nano-dielectric different from that in normal dielectric materials?
Currently, we haven't made that distinction yet. So we only consider it's being deep trapped, and there's also a possibility to have a recombination. The only thing I can think now is potentially because of the deep trap involved, and potentially relieve more energy during the recombination. So that may be bad thing for the the dielectrics.
Mm-hmm. Okay. And then we have another experimental question. Is there any other method to carry out the space charge distribution experiment without using PEA and ISPD?
Yes, there are plenty of other technical used as well, such as the thermal step method or thermal pulse method, and also this LIP method, laser-induced pressure pulse, or PE, pressure wave propagation method. There are a few. They were all sort of developed in the similar time in the 1980s, as I mentioned earlier. So yes, you can use other method to monitor the space charge in the dielectrics in general.
Mm-hmm. Then we have a last one, I think, in the chat that says, does the model apply for both homo and hetero charges?
Yes, currently we consider the injection from the electrode, and if you consider a little bit more complicated, you can also introduce this ionic charge into the system as well. But I think we can only move one step at a time, and but that's something that's for the future consideration. And when we have the ionized charge in the system, then you have a heterocharge distribution.
Mm-hmm. Okay, I think now from the audience side, we hopefully have all questions from the chat. Otherwise, please repost it or unmute yourself to ask it directly. In the meantime, I have one question that relates to this low loading regime. And so there, in effect, only a small layer of the nanoparticles close to the electrodes are needed, right, for the effect. In principle, you don't need the bulk.
Exactly. So that's why in some cases the people use nano coating,
Right.
and so that's I think that's basically a sort of a similar principle.
I was just about to ask whether there is some research going on, just looking at how to modify the surface layer.
Yes.
Okay.
Yeah.
Okay. Yeah. Then.
One more question has been added.
Yes. Yeah. You can add it. Yeah. Here I can. There's another one. You are speaking about the samples, but how do we measure if we have a few meters of high voltage cable suspected for a locally accumulated space charge? Okay. I don't. Maybe.
Yes. Okay. So currently we also, well, there's a few examples of people to measure the space charge across the real cable. So we have a system in our lab as well, allow to not the sort of 400 kV cable or above, but with a smaller size cable, we are be able to do the measurement. But in some other laboratories or industrial companies, and they have the facility to measure the real size cable.
Okay. Thank you very much. Then I think we finish with now the last question that has come in, and this is quite an interesting one, I guess. Is DC or are DC conductivity and hopping conductivity related to each other?
The conductivity, the hopping is one of the mechanisms contributing to the DC conductivity. Yeah, they are related, and but there's some other mechanism as well.
Yeah, maybe I can add something. So when people are considering the nanomaterial or micro level layer material, so there are different kind of conduction mechanism that can happen, and which is under the umbrella of DC conductivity or DC conduction mechanism, and hopping conductivity is one of them.
Yes.
So it can be the hopping or trapping or space charge conduction mechanism, or there might be the Schottky emission, and also Paul Frankel, it can be.
That's right.
So all of the conduction mechanisms may be probably bulk limited or electroc limited. They are under the umbrella of DC conductivity. So in the AC conductivity, it's different. So you cannot consider it. You have to think about differently, but hoping included inside the DC conductivity. So hope the questioner got the answer.
Mhm.
So Professor, I think I will have one question for you. On the one question, so you said about in the last few slides, I think I forgot the slide number, last slides or second last or something like that. You talked about conductivity and you said only Schottky emission and tunneling. But as you were talking about space charge characteristics in nano-dielectrics, but you did not talk about space charge conduction mechanism in nano-dielectric material. So is that you are not considering it, or it doesn't show up somehow?
Currently, as you're right, we currently, when we consider charge injection, and we mainly consider the Schottky mechanism. And while through the bulk, and currently we are using this hopping and this tunneling effect. And so what we're trying to see here is to match in the experimental results where we observe the charge distribution and with this simulation. And we are not rule out of this space charge limited current or anything. And here we're trying to sort of matching the experimental results with the simulation. And currently we are using these two sort of mechanism to simulate. But in the future, maybe if we see the discrepancy, then potentially we could explore further.
Thank you. May I ask kindly what kind of simulation tool you're using for that?
We are using what either MATLAB or Console.
Okay, console or MATLAB.
Yeah.
Thank you very much.
Okay. Yeah, if you have a last question, please unmute yourself. Otherwise, if this is not the case, I would again like to thank Professor Chen very much for this informative webinar that we had today. And yeah, I would then close the webinar and thank everyone for the participation. Yep, and
Okay,
hopefully,
thank you.
Thank you. Thank
hopefully
you,
we see
Raphael.
you
Thank you, Professor
all
Chen.
again.
Thank you.
Thank
Thank
you,
you
all
very
audience.
much.
Thank you, Professor George. It was very
Goodbye.
nice to have
Thank
this
you.
kind of
Yeah.
Bye.
webinar.
Goodbye.
Goodbye.